Tonight we have a wonderful guest with us, Dr. Blair Wolf. He's a professor of biology at UNM. You all may have heard him you may have met him at the Hummingbird Festival. Several people talked to him there, or if you were at the May program, Shane Halter's program on his hummingbird research, that was done under Blair Wolf's as a graduate advisor. So he divides his time between Members Valley, Tucson, and Albuquerque, so is quite familiar with our local bird communities. So we're happy to have him join us tonight, and I'll hand it over to you, Blair.
Okay, thank you. Can everybody hear me okay? Great, great. I want to start by sort of looking at this slide right here, and I'm going to actually read part of it to you just because it's interesting. It's from a review article published in Science in 2024. And what this review article did was they went and evaluated the internal documents from Exxon and other oil companies that were released as part of information gathering in a lawsuit. And this review article summarizes that information over 4 or 5 pages. And I just want to read you this one part. And this is the background from this paper. In 2015, investigative journalists discovered internal company memos indicating that Exxon Oil Company has known since the late 70s that its fossil fuel products could lead to global warming with dramatic environmental effects before the year 2050. Additional documents then emerged showing that the U.S. oil and gas industry's largest trade association had likewise known since at least the 1950s, as had the coal industry since at least the 1960s, and electric utilities, Total Oil Company, and GM and Ford Motor Companies since at least the 1970s. And so scholars and journalists have analyzed these documents. This is a document from 1982 from an internal Exxon research report, and it shows the years here, and this is 1960 to 2100. It shows the atmospheric carbon dioxide on this axis, starting at about 340. And then it shows the projected warming of the climate here on the right axis and the y-axis. And this document from 1982 is dead on the trajectory that we're on. And you know, the goal has been 2 degrees of warming. We're going to blow past that. You know, we're totally looking at 3 or 4 degrees Celsius of warming, which is going to be catastrophic, right? That's what my instincts tell me after looking at the data and knowing about the things that we really don't know about. We don't know about all these other things like, methane caltrates in the Atlantic Ocean or ocean circulation or what's going to happen to the permafrost. And the releases from those could add a lot of positive feedback to the system and cause climate to warm even more rapidly. I wanted to briefly talk about myself. I've been working on sort of climate change in bird communities since about 25 years ago. But I became a hardcore scientist at 19. I was not a very apt high school student. I'd rather work on my car or go chase lizards and snakes and birds in the hills. And so I was a CD student. And my dad, who was building nuclear power plants for General Electric at the time in 1975, said, "You're either going to be pumping gas or flipping burgers here in about 6 months. You may want to think about going to the Navy nuclear power program." Well, I wasn't much for following parental advice, but this one time I did. And so I ended up with a badge like this and spent 6 years in the Navy as a nuclear propulsion plant operator on a submarine and an electrician and a scuba diver. That gave me a hardcore background in science. We were actually refueling the nuclear reactor in Pascagoula, Mississippi while I was there working. And so my background in science, at 19, I was a hardcore scientist, and that gave me a good background for what I do now. And so these are some of the papers we published, this one in 2000. Actually, I was in Carlos Martinez del Rio's lab right here when I published this paper on climate change and desert birds back in 2000. I was given this document at the Hummingbird Festival, Climate Change in the National Parks. It's been banned. It's been banned. They had to give away all these pamphlets because they couldn't distribute them. So they had to get rid of them. So the whole climate change is a hoax. We know it isn't. Everybody knows it isn't. And the effects are going to be profound on our children, their children, and their children's children, right? And so I want to give you a perspective on desert birds today, because that's what I mostly study. And I'm very interested in how things work, whether it's a car or a nuclear power plant or a bird. And so I study animal physiology, how animals work. And within that context, I'm going to tell you a story about a little bit how we investigate how animals perform in the heat, and now how we can take those data and model what happens to bird communities when they're exposed to heat stress. Okay, and from there, I'll show you a couple of case studies that go into the effects on reproduction, for example. And so here's some data, interesting data. These are the record highs and lows for Phoenix by decade. And notice all these record lows here. You can't see the axis, but this is about 1950. There were no more record lows after 1960, I think, and only record highs. These are the number of days above 100 degrees by decade. And notice that this has increased radically. The number of super hot days in Phoenix that are above 115, notice starting in about 1970, these really have increased. And so there's no doubt in anyone's mind that looks at data critically that we're undergoing a rapid warming of the Earth's surface. Heat waves are the leading cause of death in the United States. A couple thousand people a year. This is due to both cardiovascular, respiratory, and heat stroke effects. So there's a variety of things that drive heat wave deaths in the US. Right now, this is often called the hockey stick figure. Here is the stable climate all the way up to 1940, 1950, and then we see this abrupt increase in environmental temperatures. This is weather, this is climate. The variability is high, but we see a clear trend. This is by Michael Mann, was the person at Penn State who produced this document. 1 degrees, we're well over 1.5 degrees now. We're headed, if we're not at 2, we're close to 2 degrees Celsius of warming already. And so, and with the current administration, there's nothing going to happen that's good as far as warming goes. So let's talk a little bit about heat waves and what's a heat wave? Well, it's a period of time where the environmental temperatures are above the 95th percentile for high temperatures. And so if we have, maximum temperatures increasing by 3 to 5 degrees Celsius by 2100, if this was the old climate, here's the new climate. And so we're going to have more record hot weather. Okay. If there's more variability, then that flattens out the curves and it pushes things up even hotter. And then we see this shift in both the mean and the variance, and we get more and more record hot weather. And so what are we seeing? Well, we're seeing data that tracks along this way. The very hot heat events we used to have would occur at a return rate of what we call 1 year in 20 years. So that event would occur about once every 20 years. Now we're seeing those events occur once every 2 years and once every 5 years. So we've had a 5-fold increase in the number of extreme events that we're seeing on a year-to-year basis here in the US. Heat waves are also a problem because they're increasing by duration. Instead of being only 4 or 5 days long, now they're 7, 8, or 9 days long. And that chronic heat stress, keep in mind that we live in a built environment where we turn on the spigot, we have water, we have power, we have all these things, but animals in the wild have to make a living every day. Right? And so they have to find food and water enough to balance their water and energy budgets on a daily basis. And they don't have much of a buffer. They might go a day, maybe 2 days if it's a large animal, but beyond that, all bets are off, right? And so this was a photo on the front of my first slide of my advertisement. These are young Costas hummingbirds. I found this nest at Saguaro Lake back in about 1995. And when I walked up to the nest, the female was sitting on the nest just like this. And she was shading her nestlings. And these nestlings, the eggs are only a gram, and the nestlings are this big. They have like 25 small drops of water in their whole body. And she flew off the nest when I arrived. I got a picture of her. She flew off the nest, and within 30 seconds, these young birds had their head up in the air and were going like this. And they weren't begging for food. The sun was hitting them, and the heat load from that sun was causing them to overheat very, very rapidly. And so they're up there panting and evaporating water as fast as they possibly can to try to cool their body and keep it below lethal limits, right? And so that's one of the things when we talk about the maintenance of body temperature, we all know that our body temperatures run 98.6 from moment to moment, right? Well, if it goes above or below that very much, we don't do well. Hummingbirds or birds in general have a more labile body temperature, and they're able to tolerate extremes, but they still are subject to heat stroke. And if the body overheats, then you get cell death and you die, right? And so they need to avoid that, and they do that by evaporative cooling, by cooling their bodies by evaporating water. We sweat, they pant, okay? So let's talk about the challenges for animals in the heat. They need to maintain their body temperatures below lethal levels. Birds are what we call endothermic homeotherms. They maintain a high stable body temperature, and they use internal heat like we do to maintain that high stable body temperature, okay? Okay, but they experience in the environment, when it's hot, they experience large heat loads. And so when the environmental temperature, when the temperature outside is higher than our body temperature, we gain heat from the environment, right? In addition to that, we've got metabolic heat we're producing that we have to get rid of. And when environmental temperatures are above our body temperature, the only way we can get rid of that heat is by evaporating water, either from our skin surface by sweating or panting. And that's what birds have to do. But this sets up a real conflict for animals living in the desert, right? They got to evaporate water to stay cool, but it's a desert where there's no water and they've got to stay hydrated at the same time. And they've got to maintain that body water pool at a pretty stable level, because if they get too dehydrated, that affects function as well. Okay? So they have high rates of evaporative water loss, lots of evaporative cooling when it's hot. Lethal dehydration is possible because most birds, as soon as it gets hot, they go find a shady place to sit like we do, right, if they're smart. And so dehydration is possible because they're not feeding or drinking during the heat of the day. They're just sitting in a cool shaded microsite. There are also chronic effects on what we call fitness, on the reproductive success of the bird and its survival. And we'll talk about those as things as we go along. And so here's some pictures of birds in different places. This bird is panting. It's a white-browed sparrow weaver in South Africa. It's evaporating water from its lungs and upper respiratory tract to stay cool. This is a little black-tailed gnatcatcher over in Arizona, sitting at the base of a large tree in a cool shaded microsite to try to stay cool. And these are mulga berries that we worked on in Australia that are, again, they've scraped a hole at the base of a tree and they're sitting in the coolest place they can find. And the air temperature is, 107 to 110 right now. So it's a little bit above their body temperature. This is what you see when animals need water during these heat waves in Australia. The koalas actually come out of the trees and will drink from your water bowls, or lay in a water bucket, or so the need for water is great for animals that live in the desert. Okay. How do birds cope with extreme heat stress? Imagine walking out on your patio and seeing this. This is an Overlander Roadhouse in Western Australia. It's a sort of a gas station complex out in the middle of nowhere. And so all these budgies the air temperature was 50 C plus, over 122, right? It's hot and dry there. These birds this is in January 2009, these birds are here in the shade trying to stay cool. Because if you're out in the sun, moving from the shade to the sun is like increasing this room temperature by about 15 or 20 degrees. That's kind of the heat load you get from sitting in the sun, right? And so these birds are sitting here on this day, and the results were a large die-off. We don't know how many tens of thousands of birds died, but this appears that there was water available, so it was the direct effects of heat stroke. Okay, the body overheating, them not being able to cool. And budgies are pretty heat tolerant. They're able to cope with heat pretty well because they are a desert bird. There are a number of other instances. This is in South Africa, where several hundred birds and bats died in a heat incident. 14 different species of birds. These die-offs are becoming more and more common across the globe in arid areas. Here's Australia, South Africa, and India. 2,000 heat wave killed 2,000 ostriches in South Africa. These are Carnaby's black cockatoos here. More than half of an endangered population was killed off by a heat wave there. And then peacocks in India, the national bird. They were having deaths from heat waves there in India. Even the United States, with poultry in the Midwest and East, those high temperatures can kill. In one farm in Redwood Falls lost 50,000 turkeys in a single day due to heat stress. And so this is a challenge for all animals. If you look at us, we're really, really good at coping with heat stress because we have sweat glands, we secrete water onto our skin surface, that water evaporates and carries away huge amounts of heat. And so we can tolerate high temperatures very, very well if we're acclimated. Other animals, not so much. Most primates can't. Rodents can't. There are things like cattle and horses that can't, but dogs can. And so this is one last thing here. These are flying foxes, these giant megabats. They roost in the trees above homes in Perth and Sydney and other places in Australia. And they aren't that heat tolerant, even though they roost out in the open like this. Air temperatures of 108 to 110 just cause them to drop in large numbers. And in one recent die-off, they had about 100,000 bats from 25 different colonies die. So we want to understand, wanting to know how animals work, I want to understand the susceptibility of different animals to heat stress and how they cope with it and what that means for animals in different environments, okay? And so here's sort of a research overview of what I'm going to talk about today. I'm going to first talk about how we assess individual species performance in the heat. How do we do risk assessments? How do we measure how well different birds perform? Because different birds perform at different levels in heat. Then I want to talk about a model of the effects of higher temperatures on heat stroke and dehydration risk in birds and show you some maps that show potential risk for different birds on different continents. And then I want to assess the effects of high temperatures on reproductive behavior. And we'll talk about some very interesting birds in Africa in the Kalahari Desert about that. They're called babblers. And then finally, we'll talk a little bit about assessing the effects of warming and drought on local populations. And I'll talk about one of my graduate students' work on burrowing owls in this part of the talk. So this just shows the maximum body temperatures in different groups of animals. If we go over here to birds, we say they can tolerate maximum body temperatures of 44 to 46 degrees. That may not mean much to you, but we're talking about 110 to 115 degrees Fahrenheit. Very high body temperature. We're long dead. At 105, we're almost dead. You wish you were dead at 105, but body temperature 105, right? Some children can tolerate it for short periods of time. 106 and up, and we're dead. Birds are what we call, they use hyperthermia. They're able to elevate their body temperature to help them save water. Because an elevated body temperature means their body temperature is closer to the environmental temperature. It's easier for them to get rid of heat without evaporating water. So this is a water saving mechanism, okay? So how do birds thermoregulate? Okay, how do they maintain a high stable body temperature over a whole wide range of environmental temperatures? Well, they do it the same way we do. Okay, and so this graph here shows the environmental temperature. That's 122. This is 104. This is in the 90s here. And this is the metabolic rate of a small bird called a verdin that I worked on one time. What I want you to see is that the metabolic rate is flat here. This is the comfort zone. This is like the bird sitting in this room where it's comfortable. It doesn't have to adjust its metabolic rate to stay hot or cold. Here we have, this is cold stress. The metabolic rate is increasing. That's shivering by the bird to stay warm. And here the bird is panting, and that's the energy cost of panting right there. The movement, the respiratory apparatus, that actually produces heat too. But the thing here that's scary are the increases in evaporative water. So this is the water that the animal's losing across its respiratory tract and skin. And this is then increase in evaporative water loss between about 104 and 120 degrees. There's a 7-fold increase in evaporation. The bird is losing 5% of its body mass an hour. in an hour or two, it's gonna be dead, right, at that kind of loss rate for water. And so this is the key thing for birds and other animals in the heat. They gotta evaporate water to stay cool. We gotta do it too. And it's actually more cost effective to carry as much water as you can if you're stuck out somewhere, rather than trying to just walk out without water. The cost of carrying a load of water is much, much less than you think, just due to the energy expenditure. So here's evaporative cooling is really expensive. That means the birds potentially dehydrate. So I'm just going to talk about how we assess the thermal biology and thermal regulation in birds. These are some of the birds we've worked on. We had a grant from the National Science Foundation. I had collaborators, Todd McWhirter in Australia and Andrew McKechnie in South Africa, and then we worked in the snoring bears of Arizona. These are some of the species we looked at. That's an owlet nightjar, a roller, a paraluxia, a galah, screech owls, all sorts, cactus wrens, all sorts of different birds. So what do we do to assess the potential of how these animals work? And so this is done in the lab. We go out in the field and set up a lab out in the field. Then we go catch birds. We hold them for 24 hours. We test their responses to heat like we would a human, and then we release them. And we measure those responses over a wide range of temperatures, and that tells us how well they cope with heat stress. To make sure we're not doing permanent damage to the bird, we actually measure their body temperature in real time, so we know they're not going to overheat. And then we have a camera on them so we can actually watch what's going on to make sure they're not in distress, right? Because we want normal responses, and birds are adapted to the heat. It gets to be 120 out in the desert. They're adapted to the heat and they can cope with it. But this is a bird held in the dark, and we're measuring its metabolism and water loss and body temperature simultaneously. And these are some of the traces you get, some of the data. And this bird's doing what we call, this is water loss right here, and this is what we call gular flutter. It's fluttering here, then it stops, the water loss drops. It's fluttering here and it drops. This produces a series of graphs like this, one that measures body temperature, one that measures evaporative cooling, the other measures its metabolic rate. Okay, and so this is for a house finch, a common poor-will, and a dove. And we're able to assess all of that and see what the relative performance is across species. What we see, and I'm not going to try to point this out to you, is that the mourning dove and the common poor-will are very thrifty in their metabolism. They don't have to produce a lot of excess heat to stay cool. And they actually maintain lower body temperatures than the house finch does. And so they're very, very effective at evaporative cooling. And so house finches have to pant to stay cool. This is a Palestine sunbird here. It's sitting on eggs in Israel, and it's actually panting to cool its eggs so the eggs don't die. So some birds actually cool their eggs. And this bird uses panting to thermoregulate, panting to stay cool, panting evac water loss. This is a Chuck Will's widow painted by John James Audubon in the 1830s. It was really detail-oriented. These are all blood vessels in the gular pouch. These animals actually flutter that gular pouch and are able to stay cool very, very efficiently. They can evaporate a lot of water, and the thing just ripples like that, almost no energy cost to that. And then finally, the white-winged doves over here, they have elaborated a mechanism of cooling using their skin. They evaporate water across the skin, somewhat like we do. They don't have sweat glands, so we don't know exactly how they do it. They're able to change the resistance of the skin so water evaporates off of it, it keeps them cool. Okay. So this is what we get when we test these birds. These are all the birds we tested, and it tells us about the birds' heat tolerance limits and how they vary. Birds with gular flutter and doves are the best. They can tolerate temperatures from 56 to 60 C, whereas the songbirds only tolerate temperatures between 44 and 52. So doves and nighthawks and things like that are tolerating temperatures of 150 degrees Fahrenheit without ill effect. They fly off. They're able to cool that effectively. Whereas songbirds, somewhere between 104, 108, and 115, something like that. And we saw this curve before. I just want to look at, this is the cost of panting in metabolism. This is metabolic rate, the cost of panting for metabolism. That's heat added to the body that the animal has to get rid of by evaporating water. Okay. Here is gular flutter. Those costs are less. Here is cutaneous water loss. The costs are almost zero. Notice this line doesn't go up like this. It stays flat. These animals are actually cooling without any metabolic costs. That saves water. So doves and nighthawks and porwills are very, very effective at evaporative cooling because they don't have high metabolic costs associated with it. So they can just focus on the environmental heat load. So now that was how we assess animal performance in the lab. Now I want to talk about modeling what happens in the field with these, using these data on evaporative water loss. And so here's here's a climate map or a map for Arizona showing the 30-year average maximum air temperatures for July. And so if we look right here, the average air temperatures there in July are 111. Okay. And if we look across the distribution here in orange, 42 to 40, we're looking at air temperatures of 108 to 104, 112. Those are the average air temperatures. Those aren't the highs in Arizona. So this is down around Gila Bend and Ajo, one of the garden spots of Arizona, if you've never been there. And so we want to model how birds and how temperature affects these birds over the landscape, right? And so we're going to use that evaporative water loss data to model that. We're going to use climate data to do that too. And then we're going to project it forward into the future to 2100. And what we want to do is look at how long it takes a bird that's sitting in the cool shaded areas to actually lose enough water to die. And so how long does it take for the bird to dehydrate? So if we say, and so here we have house finches. We assume that they're sitting up in the shade and not feeding or drinking, okay? Given the current situation, you know, and those air temperatures, you know, how long can these birds survive and how many days are there during the year where survival times are less than 5 hours? We figured that was how long they could sit without drinking, okay? And so initially, and this represents the species range in yellow for house finches. This is under the current climate. And so we see down here in Arizona along the Colorado River, about 20 to 40 days where they exceed their limits of dehydration tolerance and have the potential to not survive, okay? That's in the current climate. If we go to 2100 with 4 degrees of warming, we now see just down in the Colorado River area that the number of days has gone to 60 to 80 days where the birds potentially exceed their dehydration. And so a much broader area impacting a much larger part of the species range too, okay? Notice this area here is encompassing most of the species range. That's an 18-gram bird. We can look at a smaller bird, the lesser goldfinch. Already along the Colorado River, those birds are seeing between 40 and 60 days of extremely hot weather that could cause them to exceed their limits of dehydration tolerance. In future climates, and that's 42% of the species range, where at least one day they have an exceedance like that. In future climates, we're looking at, look at the hot spot here now on the Colorado River, looking at 80 to 120 days of exceedance. And so this is about dehydration. This is not about the birds overheating per se, but allows us to evaluate risk, right, for birds on these landscapes by species. And so we looked at this across the whole community of birds and in California, in the Mojave Desert, and found similar things that, in fact, larger birds that had higher cooling requirements actually were in decline in the Mojave Desert of California. We've done some work like this in Australia where we assessed risk in Australian birds. Shannon Conradi was a grad student with Andrew McKechnie. Andrew McKechnie is my partner in South Africa that I work with. We assessed the same kind of risk for Australian birds, for about a dozen Australian birds. And first we assessed their heat stroke risk. And so this is the current climate here for different species of birds. So here's the gray butcher bird, the galah, the spiny-cheeked honeyeater, and the zebra finch. The yellow indicates, the color indicates the number of days per year where there's an air temperature high enough to cause heat stroke death, right? Okay, and then this shows the future climates. And so the future climates for zebra finches, they go from 0 days a year or just a couple of days a year in parts of their distribution where they're potentially subject to death from heat stroke to 5 to 10 days here. Overall, we don't see big shifts in heat stroke risk across species. Mulga parrots a little bit more, and yellow-plumed honeyeater a little bit more. And so the birds are able to deal with heat stroke risk pretty well. Okay, and so because they're very good at evaporative cooling and they have very high body temperatures, even though it's hot, they can tolerate it. For lethal dehydration risk, we see a little bit different story. Here's zebra finches again. They're already seeing 40 days to 60 days in the current climate where they're at risk of dehydration in 5 hours or less. In future climates, we're seeing that risk jumps up to 80 to 100 days in much of their range. Okay. And you can look across the species from here to here, here to here, and here to here, and see how risk change. Here's the yellow-plumed honeyeater. So risk is increasing across the bird's range. And so how do we get these data? Well, we do these physiological measurements in the field, then we take that data and we map it against climate data onto a map and calculate how long they can potentially survive. So this gives us an assessment for risk across the different species. Okay, so that's how we map risk, or one of the ways. The only way you can test that is right through seeing mortality events, really, and we're hoping not to test that. Now I want to talk about some work in the Kalahari Desert that it's not my work. It's by Catherine Duplessis and Amanda Ridley. They work on these really cool birds called babblers. Okay, southern pied babblers. And they work on a place called the Kurman River Reserve. And this is, you type in Kurman River Reserve, you'll get to see meerkats. Everybody likes meerkats. You know what a meerkat is. I had meerkat pictures. I took them out because I didn't have enough time. But the interesting thing with these birds is they're very communal. They forage in large flocks. They have helpers at the nest. And they readily habituate to humans. And so all the birds are color banded. They know every individual here. And they have flocks of them that they follow. And every day they can ask the birds to weigh themselves. And so this is like the gold standard for tracking sort of body condition in birds, is what their weight is. And so by offering them a little sip of water, a little piece of egg yolk, they've trained these birds to get in a line and hop up on the scale one at a time and get weighed. They train meerkats to do the same thing. It's the funniest thing to see. You'll be standing there and there's a scale there and a meerkat, the meerkats will be all lined up. They get up in the morning, they come out of their burrow, they line them in front of the scale, and somebody stands there with a clipboard and records their weights. And then they go off and forage and catch scorpions and millipedes and all these other things all day long. And before they go to bed at night, they get weighed again. And so this is a really cool system. The cooperative nature of these birds makes it possible to do things you couldn't do out in the field, right? Because they're cooperative, they're helping you. And so we want to see how high temperatures affect these babblers, okay? And so this graph is hard to see, but this is an increase in temperature during the day. This represents here, this line is their foraging rate through the day as a function of time of day here. And so we see as it gets hotter, they forage at the same rate, which is not what I predict from working on Sonora desert birds. Usually during the heat of the day, the birds go find someplace cool and sit there, right? But these animals continue to forage throughout the day, but we see an increase in what we call heat dissipation behavior. They spend much more time panting and going like this with their wings out. And guess what? You can't forage when you're doing it. So what we do see is with these babblers is that their foraging efficiency declines. The number of insects they catch every minute decreases, okay? So that means their food intake and their water intake is decreasing too, because there's no water in the landscape in these places. They're getting their water from insects they eat. The insects are maybe 70% water, not our body composition, right? And so they're getting water from the insects they eat, okay? And so here's a group of babblers. I mean, they're really something to watch, right? They're funny because they're always together and they're always fighting and talking to each other. So here's heat dissipation behavior, how it increases with air temperature. And so we see increases with air temperature. This is 98.6. This is about 100 degrees right here. We see the amount of heat dissipation behavior increases with air temperature. Okay, they got to cool more when it's hot. Okay. Here's foraging efficiency as far as a function of temperature. Notice this is a line going down. So as it gets hot, foraging efficiency decreases. Okay, so they're collecting less food. Okay, overall, what does this do to the animals? And so here's a babbler feeding a young fledgling, right? And so they're collecting less food, which means less food for their nestlings or fledglings and less food for them. So what happens here? So what do we see? At higher air temperatures, we see a change in body mass, which is negative. And so this is the gain in body mass here. This is positive. This is negative. We see there is actually a transition point where they're in what we call positive mass balance. They are doing fine at air temperatures up to about 38. And then there's a crossover where the animals are actually losing mass. They're losing weight every day. So if their temperatures are high, they're losing weight every day. And as I said, body size or body mass for small animals is like the gold standard for how good a shape they're in, because they can go bad so quickly. Right? It doesn't take much. Loss of 10% of their body mass if they're not super fat is a lot, and they don't survive much past that. Okay. So the story here is that as air temperatures increase, their behavior changes, their foraging efficiency falls off because they've got to cool more, but they need to find more water to supply their bodies, right? But they're not foraging as well. The efficiency's down. And so they're in a negative water and energy balance, which can't persist for very long. So any chronic heat stress like that, day to day, 3-4 days in a row, and there's a super big problem, right? Okay. So that's one example of how behavior changes. Now I want to show you a story a little bit about reproductive dynamics and growing. Okay. And so here's the current drought monitor here. This was as of today, showing that we're not in extreme drought, but we're in severe drought. And this has been going on for 20 plus years, right? So the Southwest is under mega drought conditions for the last 30 years. And there's no let up in sight. And so how do birds cope with this? Because they've got to find their water and food every day out in the field, right? Unless it's a hummingbird at a feeder or something like that coming through a migration, or you're feeding birds in the yard. All right. And so this is the current conditions as far as drought stress goes. I want to talk about a project now by one of my master's students, Cruz McDonald. She worked on Kirtland Air Force Base. In the past, the military has actually been a good steward of wild lands in the past, because they own lots of land, like the Berry Goldwater bombing range, a couple million acres, other places, Yuma Proving Grounds, any number of lands. And they may fly over them, but they don't allow grazing, they don't allow mining, they don't allow intensive activity on those lands, and they're hardly impacted. And they also were mandated until recently to have these environmental monitoring programs that they had to assess the health of the ecosystem and the animals that live there. And so Kirsten was actually paid by the Air Force to monitor these sperm whale populations on Kirtland Air Force Base in an area of very intensive use by the military to see how they were doing, right? And they nest in prairie dog holes. They nest below ground. They're somewhat diurnal. You'll see them up like this on their mouths during the day, but they forage at night and hunt, and they weigh maybe 150 grams, and this populations are migratory. They come and go from probably Chihuahua, Mexico. It's probably where the wintering grounds are. And so she actually collected data on reproductive dynamics for 10 years, which is unbelievable for a master's degree. 10 years of data is incredible data set. Detailed reproductive behavior data. So when did they arrive? When did they pair? when did the female start laying eggs, how many offspring were produced, how many survived, all these kinds of over a 10-year period. Okay. And so she came to me with these data and said, hey, I want to get a master's degree. I'm like, okay, you've already done all the hard work. Now it's putting it within the context of, you know, whatever questions we want to ask and see what we can do. So she came and worked on a growing owl. So here's the habitat up in Albuquerque on Kirtland Air Force Base. A nice thing about Kirtland is it's basically on the airport, on the Albuquerque airport. And so these are weather station data from the Albuquerque airport, which shows air temperatures and variability year to year and season to season. And we see, here's the 30-year trend right here, and all of a sudden we see this increase. So we had 1.5 degrees of warming over an 8-year period at Kirtland. Precipitation, we see the variability in high variability, right? High variability in precipitation, but we also see the onset of a really severe drought here in about 1984, right? And it's still continuing, right? As we know. So here we have drought and warming at the same time. What happens to the owl reproduction? Okay. And so here we have precipitation. And so this is the number of breeding pairs that she was tracking. So there's a known area she was tracking. There's a number of breeding pairs. Here's the first year, and here's the last year of data. Here's precipitation. This is the amount of rainfall by year. And here's the number of owl pairs. Started at 50 pairs of owls on the site. Seesaws with precipitation. I mean, this tracks incredibly well for ecological data. I mean, I was just amazed at this, all the way down to 1 pair, 2013. So they went from 50 pairs of owls breeding on the site to 1 pair. They've rebounded somewhat now, but they aren't nearly at 50 pairs. Okay. And so a precipitous decrease with drought. How do they respond to temperature? So remember, the temperature is increasing and the precipitation is decreasing. This is a bad thing for ecosystem processes, because if you take water away from an ecosystem, plants don't grow, right? At the same time, if you warm that system at the same time, you're reducing the amount of water coming into it. The warming, even modest warming, causes what we call the soil moisture to fall greatly in the soil. And so you get even less plant growth. We call that net primary productivity, okay? And if plants grow, then animals eat them, okay? But if there's no plant growth, then the animals can't eat them. And so these are predatory animals. They've got to have something to eat. So the insects and mice and lizards and things that they eat, if the NPP is low, if the productivity is low, then there's going to be low numbers of those too, right? And so here we see temperature increasing, zigzagging back and forth. And notice that as temperature increases, the number of owl pairs decrease. As temperature, number of owl pairs go up, as temperature increases again, and we get a decrease in the number of owl pairs. So that's the trend in the data. Here's a sort of an integrated look at both precipitation and temperature. Okay, and so this is the previous 2 years precipitation. Okay, between and this provided the best sort of model fit for what was going on in the number of pairs. Here we have the number of breeding pairs. Each one of these represents a year in the number of breeding pairs. And so the highest number of breeding pairs was in 2008, 1999. And then the color of these symbols is temperature. And so we see in years with low precipitation that were very hot, we see very few breeding pairs. In years with high precipitation, even if they were warm, we still see lots of breeding pairs. And so there's a real effect of both precipitation and temperature on the number of pairs of owls breeding in the system. Okay. This is the number of fledglings per breeding pairs. So this is the number of offspring. Owls are interesting birds because they practice this behavior called facultative brood reduction. Owls can lay a wide range of number of eggs. Burrowing owls might lay anywhere from 3 eggs to 9 or 10 eggs, depending on the given year. Okay. And if it looks like it's going to be a good year, if they sense physiologically it's going to be a good year, they might lay a whole bunch of eggs. These birds lay, as do most birds, they lay one egg a day. Okay. So one egg is laid a day. After the last egg is laid, or near the last couple of eggs are laid, the female starts warming the eggs near the end of that clutch. Okay. And so because the eggs are warmed a little bit near the end before all the eggs are laid, we have a thing called hatching asynchrony. Where all the eggs don't hatch simultaneously. They don't all pip out like ducks and all hatch at the same time. They may hatch over a 24 or 36-hour period, which means that the eggs that hatch first, those young are fed the most and they grow fastest. The eggs that hatch last, the young are smaller and don't get fed as much because they got to compete with the other nestlings in the clutch, right? And so what happens is if you start out with a good year and then things go bad during the nestling period, well, there's different size cohorts within that brood, and the big nestlings are able to overcome and compete against the small nestlings, and so the small nestlings don't get fed and they die. Okay, that's called facultative brood reduction, where the brood size is actually adjusted in real time based on the resource availability. So there's lots of resources. They may fledge 6 or 7 birds, young birds. If there's not many resources, they may lay 6 or 7 eggs, but they only fledge 1 or 2. Okay, and that's what happens with owls and herons and storks and things like that. And so here we see there's precipitation here, and here's the number of fledglings, and this tracks pretty closely the number of fledglings here. This is the number of fledglings per breeding pair. The owls are a little bit harder to know how many eggs they laid because they're burrowing owls, they're living in burrows, they're nesting in the burrows, and it's kind of magic. You don't see the clutch, you don't see the number of eggs. You can sort of figure out when she started sitting on the eggs, but you only see what appears above ground. That's what we see. And so there could have been 10 eggs and only 3 birds appear above ground, but you can assess the number of birds that were there at any given time. So number of fledglings falls off. This intensive monitoring allowed them to do one more key thing, was they were able to measure prey availability. And so these are animals that feed on the ground or off the ground. And so they got these little cans and they set out what they call pitfall traps. So little coffee cans filled with water, and they set them into the ground so that they're flush with the ground. And then insects and beetles and other things run along and they fall into them, right? They drown, and you can count them and assess the prey biomass, how much food there is based on how much precipitation there's been or how hot it's been. And so they're able to assess, which is a key thing here, is assessing prey availability, because that's the fuel that allows those little owls to grow up, right? And so here they assessed arthropod biomass in grams from these traps. Here's the precipitation. Here's the prey. So as precipitation drops, the prey availability drops. As precipitation goes up, the prey availability goes up. Here it is. Here's the prey in grams related to precipitation. This is a pretty strong fit. So what happens? So we see that prey has, the amount of prey is directly tied to precipitation, which explains in part not very good reproductive success when precipitation stuff. Okay. So a few more things here. One is that we saw changes in owl body mass. This is from 1998 to 2012. Overall, the body mass, the total mass of the owls fell by about 12% for 15% for females, 12% for males, and the juveniles were smaller. So the persistent drought actually affected the size of the animals during their breeding season. And as I said before, size, body size is the indicator for birds of condition, of how well they're getting along. Okay? We also saw delays in breeding phenology. Between 2005 and 2013, the male's arrival on the breeding grounds were delayed by almost a month, 25 days. Pair formation was delayed by 22 days. They were late by 22 days compared to 2005. Nest initiation lagged by 13 days, and then hatching was delayed by 9 days. In general, the earlier you breed, the better you do. Their timing of breeding is synchronized to resource availability. so that when the resources are flush, there's lots of resources in the environment, you have nestlings in the nest that are being bred. Okay. These delays don't bode well for the reproductive output of the birds. Okay. And so this is a problem. So if we look at overall, we saw a dramatic population decline, 52 pairs to 1 pair in 7 years, a decline in productivity and nest success, low nest success in those later years, significant loss of body mass, an unexpected delay in breeding phenology. This was the largest reported in the literature. Delay in breeding phenology was ever been said. Okay. And so overall, I hope I sort of showed you how we might assess animal performance in the field, and then sort of map and do some predictive mapping of how that works in the future, and how the sort of the downstream effects of warming and added with drought can affect animal reproductive success in their behavior. Okay. You might think that they could evolve out of this. No, the climate is changing much too rapidly. Some estimates suggest, this paper by Quintero and John Weens at U of A suggest that the climatic niche evolution rates, the rate at which the climate's evolving, changing, is 10,000 times more rapid than the rate at which the animals can evolve. And so what are their choices then? Well, they either move or they persist. Can they persist? Persistence, that's either rapid evolution or they've got to have the plasticity built into them that allows them to be flexible enough to cope with those extremes in the environment. And that may happen with some populations, but not with others, right? We just don't know at this point. So with that, I think I'm going to wrap up here. I don't want to ignore these other parts of the globe. The Arctic areas are warming about 4 times more rapidly than our regions of the world. And those effects are going to be more profound. This is changes in annual sea ice minimum in the Arctic. You can watch this trend. This St. Lawrence Seaway will be open. We'll be running ships through there before you know it, right? And so look at the changes, the diminishment of the sea. This is the sea ice, minimum sea ice fall here. This is a figure from February 2016. This is what we call the anomaly, how far from the average temperature the temperatures are globally for February. Notice the Arctic regions are 11 degrees Celsius, almost 20 degrees Fahrenheit warmer than they are based on the long-term average. 20 degrees. This has profound effects on wildlife and the whole ecosystem, right? And so we've got to really pay attention to those regions as well. I want to thank the National Science Foundation and all of the students that helped with this. This research has been funded by the National Science Foundation off and on for me for the last 20 years. The National Science Foundation finances basic research in the sciences, in physics and math and chemistry and geology. It's got a budget of about $8 billion. It costs individual people hardly nothing. Yet, what do? We train students. This is payday. These kids are all holding up payday candy bars. This is payday in the Kalahari Desert. And so these are South African students here. This is actually a retired cardiovascular surgeon. That's Bill Talbot from the Hummingbird Festival. He was over there. And then a postdoc, he's a professor at UMass Amherst. This guy's actually an electrical engineer from Stanford. He came back to school to get his PhD in biology. And Mateo Garcia was an undergraduate in my lab. He got to go to both Australia and Africa. And now he's an ER physician in Albuquerque. So that money provides training for students and it does public good, right? And we need to support it. In my mind, as a scientist, we need to believe in science and not another BS we're seeing all the time now. Thanks very much. I'll take questions if there's some. I'm sorry it wasn't an uplifting talk. I'm hoping I can give an uplifting talk someday. But I'm worried about my children and your children and their children's children and all the generations that will come after us.
And the birds.
And the birds too, yes. No, and that's just one taxa. I mean, I work on mammals and reptiles as well. This is, and insects, and so this is just a sampler, right, of what's going on. And it's Carlos and I are mechanistic biologists. We want to understand how animals work and then how they interact with the environment in different ways. And how that allows, and climate change is a perfect context to look at those kinds of things, unfortunately. Yeah, well.
I know it's hard to separate them, but I almost felt like the precipitation was even more of an issue based on your talk than the temperature increase. Is that?
If you're a plant physiologist, there are definite relationships between soil moisture and temperature. I think it falls about 7% per degree or something like that. And so precipitation, it's either, I mean, we live in an environment where we have bimodal precipitation, right? We have the summer monsoon, which is pretty reliable, and the winter rains, which are much more unpredictable. The winter rains fuel all the forbs you see around you, basically in the trees, right? They fuel the growth of that biomass. The summer monsoon fuels the grasses that we see out here. That's all biomass that animals eat. And right now we're in a long-term drying camp, and winter precipitation is getting less and less, more and more unpredictable. We don't know what's happening with the monsoon yet, frankly. We got a good monsoon here. It was really late though. I think there may be a later monsoon, maybe one of the trends we're going to see. But over in Phoenix, they've got almost nothing, and it's the second year in a row. And the long-term drought effects of that. It's the chronic stressors on animal populations, right? Because there's things like toads that are underground now, right? That can only stay underground for a couple of few years without coming out and feeding. If there's no monsoon, they don't come out and feed and reproduce. And so they dehydrate and die underground, right? And so there's things like that going on that we don't know about, right? And so it's been a privilege to be able to study the natural world for the last 25 years. To get to do this for a living, you know, is a privilege, especially after having spent 6 years in the Navy on a submarine, right? That teaches you to appreciate the outdoors. Yeah, I saw the Bahamas through a periscope once. That was the foreign port I got to visit. Other questions? Yeah.
So I know earlier in the presentation, you said you were taking these birds and monitoring responses. What besides the glue are you really tracking?
So we measure how much water they're losing. That tells us about their cooling. We measure metabolism, right? We're sitting here metabolizing right now. Each of us expend about the same amount of energy as a 100-watt light bulb, just sitting here. So some of us are brighter than others, but you know, depending on the metabolic rates, right? 100-watt light bulb. So we measure metabolism, resting metabolism, as a function of temperature. Because for birds that pant, it costs a lot of energy to stay cool, because going like that uses a lot of energy. It produces heat, but you've then got to get rid of with water. If you sweat, I mean, we're the ideal desert animal, right? As long as we have water, we're good. But we got to have water. We don't tolerate hypohydration. We don't tolerate dehydration well at all. You lose a liter of water or a quart of water, you lose a couple of quarts, and you're in real trouble really, really quickly. Things start to shut down. You have cognitive impairment. You can't cool. So humans, as long as they're hydrated, are super high performance.
So you didn't mention much about dispersal. I'm thinking about what the hell can we do? And one of the things I keep on thinking is habitat health and heterogeneity.
Right.
Whether they are refugia, riparian areas, movement up and down large landscapes that we need to conserve. Can you just?
Yeah, I think thermal refugia is one of the big things, right? And so the birds, I saw you to show you those parrots sitting on the ground. It's really weird to be walking along and look at the base of a big ironwood tree or something like that. It's 110 out. And there's an owl sitting down there at the base of it. And it scraped out the dirt. It's just sitting there. And alfalfa just sitting there cooling. And so there are thermal refugia, and so heterogeneity, the variability we see in these environments is good. We want to try to maintain that, right? the enemy of that is homogeneity, where everything just collapses and you have a monotypic environment, right? That has no variability. So that, I mean, in built landscapes, water on the landscape is obviously helpful, right? Arizona Game and Fish has put out about 1,000 water catchments for big game out in the desert, out in the snowy desert. And birds and bats utilize those extensively. The resident birds utilize those extensively. We've actually done tracer studies where we caught birds at different distances away from those water holes and looked at the influence of those water holes. And it's pretty important in some areas. For some birds don't touch it. But yeah, no, it's habitat and
I'm just another curious, that's what I think funny, which is, are there altitudinal movements that are driven by heat?
are there what?
Altitudinal movements that are
Oh.
driven by heat. And it would be so interesting, it's so important for our area, when you have sky islands.
With the Sky Islands, certainly, I mean, I would, these lowland desert habitats, I think the birds are pretty much homebodies and they stay on their all-purpose territory all year round.
But you do see the population of certain desert dwellers, because I've lived in the Sonora Desert.
Yeah.
Now I live at 7,000 feet.
Yeah,
And we do notice that there are desert dwelling birds that are moving up the mountains.
sure they
You
are.
know, we are seeing many more, what do you call those things, the chickadee ones, roadrunners, phenocapilla,
Okay.
quail, things like that, that weren't at 7,000 feet 10 years ago, 20 years ago in our neck.
The problem with the Sky Islands is there's a bunch of stuff that live on the top of them right now. And as that heat moves up and changes the habitat type, they're gonna get burned off the tops, right?
Oh, yeah.
And those tend to be on the Sky Islands, those tend to be rare species that have limited distributions. And so once you burn out the top of that mountain, and so some of the extinctions we're seeing in Australia, for example, some of the possums and stuff are due to that. They get burned off the top of the mountains and then they're gone. You have 4 populations on the tops of mountains and it gets hot. We're done.
Wow.
So that's a good observation though. Those are the kinds of data we need. And there's an app called iNaturalist, which my son is enamored with. He's got 30,000 observations on it. He was posting 100 a day while he was in Panama for the last 2 weeks. And there's another app called eBird. The observations you make on those 2 apps are going to collect the kinds of data you're talking about now that show movements,
Yeah.
altitudinal
We
movements.
saw unusual things this last year.
Yeah. Where do you live in the Catalina?
Saltos.
Oh, here,
Yeah,
okay.
and so in like 1 week, all of a sudden, instead of like 1 western tanager, we had 5 western tanagers in the yard and lapis lazuli.
And they're passing
They are,
through right
yeah,
now.
passing through, but we never saw them in the snow, so. Weird.
Other question?
So I used to live in Albuquerque, and go down to the river all the time. And in the last 5 to 10 years, certainly the last 5 to see far to the along the river and or even in the same basin.
There's been recent assessments done that show a loss of 4 billion birds since 1970. And so 30% of the biomass of birds in North America are gone. Right, these birds I show you, the owls, the growing owls, they're in severe decline. Another master's student worked on shrikes out there and was paid the same way. She's got a beautiful data set on shrikes that we also published. They do something a little bit different. It's interesting. Their population actually increased over a period of time. So there must be some differences in prey partitioning or effort or something going on with them. But yeah, I mean, we're in a crisis. It's both habitat loss, climate change, windows and cats that are outdoors. You just go down the list, pesticides, nicotine, pesticides in our field migration. We need to manage these landscapes and we need a federal government that has biologists and toxicologists and people that can actually assess what's going on in the environment, right? And whether it's climate or weather too, right?
I don't know if this is an unusual observation, but I actually saw shrikes herding smaller birds into the windows
Oh,
So they would get hung out on the window and then trace.
I'm not surprised. Birds are smart. You see this with Cooper's hawks. I've seen Harris hawks do this in Tucson. I haven't heard of shrikes doing it before. But these predators are resourceful, right? They're smart and they're gonna, it's like having a house cat around. It's gonna figure out how to kill something if it can. And whether it's bouncing it off a window first before it picks it up. You know, it's called tool use, right?
I assume there are there people studying diet adaptation in some of these species who are moving in a different.
Well, it takes money to do that,
Hmm,
right? I mean, not everybody's, I mean, when I retire, I may be doing stuff like that, but. You know, I mean, the ideal thing is we pay students and train students to do this, right? And produce the next generation of environmental biologists and conservationists. That's the ideal thing, but that's getting harder and harder to do right now.
Yeah, I should mention that NSF lost 50% of its funding over its 2 months. So, and all the work that we did.
Yeah.
was from that.
And the National Science Foundation, you know, you would think $8 billion is a lot of money. Well, that funds all the research in chemistry and math and geosciences and biology across all different fields of biology. Well, their overhead rate, the amount, so it's $8 billion to fund all of that, which is a minuscule amount if you look at what you're paying in taxes to fund the National Science Foundation, compared to the defense budget or compared to ICE now, right? ICE just got $120 billion or something like that. But if you look at that, only 7% of that money goes into overhead. The National Science Foundation runs their entire operation on a 7% overhead. That's what the cost for staffing at NSF. 7% of the total budget. There is no other agency that I know of in the federal government that's that efficient. There's overhead associated with the grants. That's an entirely different thing. But their overhead for their actual staffing to run all the programs is 7%, which that is government efficiency. I'm preaching, sorry.
This is kind of a weather question, but it looked like you were saying the North Pole area, the amount of ice was shrinking compared to the South Pole. Is that fair?
Yeah, diminishment right now in the northern sea ice is 30 or 40%. It's down a couple percent in Antarctica. But we may be heading towards tipping points there too. There are ice shelves that are being propped up and being prevented from actually sliding into the sea. And once those start to collapse, you know, all bets are off for sea level rise. I mean, Greenland can give us, I think, a couple hundred feet of sea level rise, something like that. I forget what it is now. And Greenland certainly got it, but, you know, it's just, if you look at the rates at which, you know, you don't want to buy property in Florida. Try to pass it on to your kids. Most of Florida's in the end underwater.
Mar-a-Lago too.
Oh, most certainly.
Soon enough.
Yeah, Megan.
This might be depressing because of their small body size, but can you speak a little bit on hummingbirds and what predicts how that works? Like, is their ability to go in the torque and any benefit in forming?
Well, I think it is. It saves energy and water overnight. So it is kind of a superpower. They can sort of go into suspended animation right overnight and really minimize the costs, energy costs, and their water costs. During the daytime, they're feeding on a nectar diet, which is 90% water. So they're going to have enough water as long as they can find flowers. I'm more worried about floral resources and floral deserts where there are just no flowers.
It's just like Comic-Con. We got the data this morning from Shane, and if they don't have flowers, normally if they are at rest, and the temperature is low, the amount of water becomes metabolically fat, compensates for the amount of water that they're using, especially at low temperatures. If the temperature is higher than 34 degrees C, which is not horrible, they are in water deficit beginning flowers. And they last just a few hours.
And that's just in the 90s. So that's
This is from this morning's data analysis from Shane. So
yeah. So Carlos is on Shane's committee as well. So
Yeah, he just sent me the graphs this morning and I was both really happy because it's a terrific scientific result and freaking.
Shane's my last graduate student. He's a retired Air Force officer, did 24 years in the Air Force. Decided his brain wasn't dead, so got a degree in anthropology at 56. And he's just finishing a PhD at Carlson on hummingbird torpor and migration. He used to fly around on C-130s as a navigator. Now he flies hummingbirds and drones.
Yeah, well, it's really good to be able to give you this answer from something now.
Right.
Yeah.
Anecdotally, it seems like the hummingbirds left here locally.
They just left. Right?
Yeah, but usually they're here a couple weeks later. And there's been fewer, everybody in London has had fewer than previous years.
We should start a Twitter account for the area. For conversation. If anybody's interested, I can coordinate it. I'm sorry, this is really geeky.
No, that's fine.
But I have a method from how much they get with nectar resources to count how many there are from each species. It works for instances. So if people want to do that, we can coordinate something to start next week. I think it would be lovely to do.
So Megan, did I not win anything?
You win our love for. No, also there's cookies over there.
Oh, there's cookies too. Okay, well, thank you very much, everybody. And,
Yeah, grab some snacks on the way out.
Yeah.
Just talking about Richard today.
Oh, thank you.
finishing up what we
Oh,
Yeah. Hey, Jim.
Oh, you remember
Good
me?
to see you, absolutely.
Yeah, good to see you.
Watched Three Gun Springs twice last week.
You did?
I did. I didn't see you up there.
No, I'm down here.
I know.
I've been going other places. I was in the middle spot 2 days ago.
Oh, really? Nice.
But anyway, I wanted to ask this question.
Yeah.
I can't.
I got involved with the Natural History Organization. And because of that, all these people were that dug in and used it. We're gonna do it in 2027 instead of 2022.
Okay.
Right.
Yeah.
And we're supposed to 27 and I have to talk other people into it, and I wish I forgot.
You know my friends Marlos and Martha? This is Jim McGrath. He's a botanist. He's a botanist who was working for the forest here recently. But I met him on hiking trails in Albuquerque.
I'm surprised you.
Oh, absolutely. I meet him on the Three Gun Springs Trail in the south end of the.
Yeah, that was my go-to trail until I got the job with the National Forest.
So he's still working for Gila National Forest?
No,
They laid you off?
did not, me and the started putting higher seats here. And actually, you can't believe that when I hear them, they already decided to select. Yeah, but, you know, at my age, my can they do that? That's what I'm saying tonight. I know, tell my.
Well, this is nice and popular. Call me doctor.
But then,
I mean,
no,
I guess it's good news.
I served that's what I was coming
Right, right. That's got to be. Yeah. But nice. Also turning current. Yeah. You know, UK is gonna get 20 degrees colder.
There's no point. I got this crazy email today. This note that they published this thing.
Yeah, I know. I got. Yeah. Department of Agriculture, they do the same thing. Yeah, liberal, yeah, radicals, yeah, that's what we're trying to do. USDA, yeah.
Yeah, the festival. I might have had a conversation with you about that.
I mean, he's hired those people that are
So excited. There was also. Yeah, it's convert like this, so it's not even a band, that's just cool.
Down the list. EPA's rolled on, interior, Bitcoin. So we're gonna do whatever you guys for the Zach Rancher. Right now. Pretty good comments.
I just was showing faces. We're talking about what she did. We should all say, like, oh man, I got his contact information. But I'm never gonna. Awesome, will do, and Carlos. Thank you. Cool. See you soon.
Yeah. Maybe I'll see you soon.
Maybe
I will turn that on and start packing this.
Yeah, no,
I should.
Turn next.
Okay.
seven.
Okay.
I'm probably here.
That's moose. Arabian quarter.
Because I'm totally fine.
I'm fine. I mean,
That's not.
Judy.
Right.
you know, I can.
Step forward. That's Judy's new horse.
Give all that. And I know.
It's a 6-year-old Arabian quarter horse.
I appreciate it.
Yeah. Oh, no, that was already off.
And Scotsman training.
I'm just gonna put it out on Tuesday.
Yeah, just.
So he's been training.
Sweet Prince.
We're gonna get.
That was a great presentation.
I think he is. Because she's getting more enamored with the arena.
You know, it's like that mix of like I'm excited, but I'm also like existential dread. There's a
Stuff twice a week.
It's like, oh man, is conservation gonna be outlawed when I get to grad school?
No fun.
Yeah.
Yeah.
That's a
You guys might see me at
10,000 for.
so.
It's not fully trained. It's gonna grow with it. And Scott is
Like the two.
On campus when I was taking biology last spring, and so I got a picture. I went up what Ravens those. We went to talk to some of the kids at Copery the other week. They were just absolutely flabbergasted. We got a picture.
That's my,
Absolutely. Me too. You know?
no, I mean, it's. Yeah.
There's been some giant flocks.
He's like, well, just sell me moose.
You know, it was one where they were just all going by in a line, so I was counting them. I think I got to like 20 or something.
Yeah.
Yeah, that's nothing. You're gonna pay every year.
Well, that's the thing, so you can keep it, it's not serious out. If it helps,
Yeah.
all the upkeep, you
Yeah.
can get it for free.
Yeah.
Pay for feed and the regular stuff.
It's still very expensive.
Yes, exactly. I don't know any of that.
Try to be.
But she's looking for an insurance company. Do you have one?
The best thing, one of the things she could do is look at, there's this company that these tax supplements. Get their digestive, look at your size of a colic. Pretty much $10,000. That's one thing. No, she should talk about,
Okay.
no, who insurance versus we don't.
Yeah.
Right?
Well, she just wanted to pay all the medical. Right, out of pocket. Depending on what medical insurance costs. I don't know, we have it on the cap, it's only 15. They pay for half.
Yeah, I don't know what you're saying, but that's not very cheap.
No, it's fine.
All sorts of shenanigans. Parallel monitors.
Yeah, yes, she just told me yesterday, she wrote me every day, and he's big.
Is
Bigger than your.
It's bigger than the man.
Yeah.
that person?
Well, she's been telling me for years, I just want a little.
Fantastic.
I want a little.
I love her.
She fell in love with this one.
She got.
Let's go back. I got
I'm not gonna be able to. You gave a very good. It was very information dense. Very
Right now.
But it was very sad.
I can't turn it down.
Yeah. Gosh, that's awesome. Yeah, she's.
I cannot make it
It's just like the intro to animal and.
But I know, it's all.
Yeah, she gets all the fun ones.
Yeah.
Okay, see ya.
Yeah.
Yeah, see you this weekend. Yeah, before I come over, yeah, I'll bring him a pastry or something.
Hey.
How are ya?
Che Guevara outing. Is it crowded?
I didn't go. What?
Oh, you didn't?
No, my son is down in San. Oh, I didn't do the motorcycle ride. Yeah.
You were talking.
No, I was
about
going to,
the
yes.
line.
I was going to, and I just couldn't swim it. They were gone for 8 weeks. They rode all the way from Santiago, did a whole loop
Wow.
over into Patagonia.
Yeah.
But I did buy a motorcycle, which I'm gonna ship down there and do a Che Guevara ride.
Sometime.
Yeah, sometime. I'm retiring next year. I've already
Oh, yeah.
decided.
Uh-huh.
I'm gonna teach one more fall semester.
Yeah.
I'm teaching ornithology right now and a physiology course.
Yeah.
And, but then I'm done.
Oh.
Yeah.
Yeah.
Oh,
I don't wanna go down to the
that's
review.
what it is.
You can
That,
definitely.
okay, got it.
So look at me, I'm a true botanist. I'm like carrying this around like a fidget.
I've been down the last 2 weeks.
Okay, did this
100 posts a day to high natural.
and
Sorry.